Hey, I'm Gouda Demi-Sue, and today we're going to pull back the curtain on the magic that happens every time you move, resize, or rotate something on your screen. And you'll see the math behind it all is actually way simpler than you might think. So let's jump right in.
I mean, think about it for a second. You click on a logo, you drag it, and it just glides across the screen. You pull on a corner, and it scales up perfectly. It feels totally intuitive, almost like magic, right? But underneath all that smooth, user-friendly magic, well, there's a bunch of really simple, really clear math making it all happen.
And the name for that magic? It's called geometrical transformations. It's just a fancy term for the rules we use to tell a computer how to change an object's position, where it's facing, or, its size. It's basically the language of digital movement.
So, how in the world does a computer handle all this for millions of pixels at once without just freezing? Well, the answer is this really clever, really efficient shortcut.
So here's the secret sauce. Instead of the slow way, calculating a new spot for every single pixel, which would be millions of calculations, the computer does something way smarter. It just keeps track of the corners, what we call the vertices. And then it just connects the dots. And that is the key takeaway here. Seriously, just forget about the millions of pixels filling up the shape. All the real work, all the magic is just happening to those few little endpoints. Everything else just kind of tags along for the ride.
All right, so let's break this down. We'll start with the most basic tool you use every single day, the Move tool. Now, in the world of math, this has a name, translation.
So you can see what's happening here perfectly. On the left, you've got the shape with its top corners at, say, 4, 5, and 7, 5. Then after we translate it, you see on the right, they've just shifted. Now they're at 7, 1 and 10, 1. The shape itself, it's exactly the same. It's just in a new spot.
And you want to know the crazy math behind all this? It's just addition. Yeah, that's it. To move that shape, the computer literally just adds a number to the x-coordinate of every corner and another number to the y-coordinate. That's all. Moving a complex object is basically just grade school math.
Okay, so that's moving. Let's build on that and talk about the next tool in the box. You know when you grab that little corner handle and drag to resize something? That's what we call scaling.
So look what happens when we scale that same shape down. Two things are going on. First, obviously, it gets smaller. But check out its position. The whole thing also moved closer to the origin, that 0, 0 point on the graph. And that's a really key thing to remember about how scaling works.
So if moving an object, translation, was all about addition, while scaling is all about multiplication, the computer just takes every single coordinate, both x and y, and multiplies it by the same number. We just call that number the scale factor. And the rules for this are super simple. A scale factor bigger than 1 makes the object bigger. A factor less than 1, like 0.5, makes it smaller. And here's the crucial part. This all happens from a fixed point, which is called the center of enlargement. You can think of it like an anchor that the object grows or shrinks from.
All right, so we've covered moving, and we've covered resizing. What's the last member of that big three? The tool you're always using in your design work? Of course, it's rotation.
And here we go. Rotation in action. You can see the object just pivots around a fixed point. In this case, the triangle turns 90 degrees clockwise, and then it goes another 90 degrees for a complete 180-degree flip from where it started.
Now, rotation, it's a little needier than the other two. To make a rotation happen, the computer has to know three things. First, what's the center point it's supposed to spin around? Second, what's the angle, like 90 degrees or 180? And third, which direction? Are we going clockwise or counterclockwise?
Okay, now we get to the really important part. On their own, these tools are dead simple. But let's be real. In any actual design project, you're not just doing one thing. You're moving, then scaling, then rotating, all at once. And when you start combining them, you discover a rule that can either save you a ton of headache or completely mess up your work. So, let's just ask it straight up. Let's say you've got to scale a logo down and then move it into place. Does it matter which one you do first? I mean, will you get the same result if you move it and then scale it? Your gut might say, yeah, of course. But the answer is actually no. Not at all.
So let's do a quick experiment to prove it. We're going to take this object and do two things to it. First, we'll reflect it, which is just like flipping it in a mirror over that vertical y-axis. Then we'll translate it, which, as we know, just means moving it to the right.
Okay, scenario 1. First, we reflect. It flips right over the other side of that y-axis. Then we move it to the right. Now keep a close eye on exactly where that thing lands. Okay, now let's rewind and swap the order. This time, first we move the object to the right, and then we reflect it over the y-axis. And whoa, look at that. It's in a totally different spot. This is proof positive the order you do things in completely changes the final result.
So this shows a really fundamental property in math. These operations are not commutative, and that's just a fancy word that means order matters. A plus B is the same as B plus A, but for this stuff, it's not. And for your actual design work, this is huge. It means scaling an object and then rotating it will give you a totally different result than if you rotate it first and then scale it. All right, so let's tie this all together. What are the big takeaways? First, the super powerful tools in your favorite design app, they're powered by incredibly simple math. We're talking basic addition and multiplication. Second, computers are smart about it. They work efficiently by only worrying about the corners of an object, not every single pixel. And finally, and this is the one to really remember, the order you apply transformations in isn't just a small detail. It's absolutely critical.
You know, every single thing we've talked about today, addition for moving, multiplication for scaling, those are the absolute building blocks for the entire 2D world on our screens. And it really makes you think, right? If these simple rules build our flat world, what happens when we jump into 3D? When you add that extra dimension of depth, how do these simple rules have to change and evolve? Something to chew on. Thanks so much for joining me.